This presentation is delivered by the Stanford Center for Professional Development.
All right, any questions administratively, things that are going on? I had one student come and hang out with me on Friday, and I had some of my staff members. So I'm hoping that was just because it was such last minute and you guys were all off skiing and doing something fun this weekend. But this Friday, I don't have a meeting, so put it on your calendars now for Friday hanging out. All right, C++ libraries. So the notion of a library is really nothing more than saying you've got some functionality that you want to provide to all users of C++ or all students enrolled in cs106, and that there is kind of some reasonable grouping to these things. You have a bunch of operations that operate on strings, or that allow you to do graphic works, or allow you to do event handling or something. And so the library is the packaging device in C++, where you say, well, here's a set of routines. Typically, it comes with two pieces. One is the interface or declaration or header file, we'll call that. And it tells you about what routines are in there. What are their names? What are the prototypes? How do you use them? You know, it often contains good comments about the things you would need to know as a client using that facility, how to use it effectively and correctly. And then there is the code that really implements it, that when you make the call to a substring operation, how does it actually work? Well, there's some code that backs it that actually does the operation that gets called at runtime when you make a call to that function. The libraries that we're going to see this quarter form roughly two big groups, right? The C++ standard libraries, so things that come with every C++ compiler. So no matter where you continue coding in C++, you will always find things like the C++ string, the C++ IO stream, the file stream, which is the F stream. There's a math header. There are headers that deal with all sorts of other facilities that are kind of beyond what we're doing here, but these are the ones that we'll see most commonly in the early part are string and stream. The typical include for them is going to be the angle brackets. That's the sign to the compiler. We're looking for something from the standard header locations. And one way to remind yourself about how to distinguish these from our special libraries is that you're going to see these very terse and lowercase names. Kind of part of the legacy of C and C++ was as a professional programmer's tool, they tended to value kind of terseness over any kind of verbose and descriptive names, making it a little easier to type, a little faster to get your point across. So things like the cout, which is the console out stream, the get line, the substr call, there's the substring name of the function there, tend to be short, tend to throw away vowels where they can, tend to be all lowercase. So whenever you're looking at a routine, you might wonder where it comes from. If it has this capitalization scheme, it's likely to be something coming out of the standard libraries. In addition to what we have present in the standard, we also have about 7 libraries that we've included as part of just CS106, mostly to make our lives a little bit easier, to provide us some convenience. Things like the random library or the simple IO library, they actually layer on existing functionality that is already present in the standard libraries, but the way the functionality is expressed in the standard is just a little bit awkward or unhelpful for the kind of tasks we need to do, so we've provided a layer that kind of cleans it up for you. The graphics is a good example of where there is no graphics library included in standard C++. So if you're working on graphics on Windows, you have access to a different toolkit than you do on the Mac or on Linux or some other platform. We have try to abstract out a very simple graphics library, right, that we can run on both Mac and Windows that then we provide one interface through that actually in turn talks to your platform in its native language to make those windows and drawing things happen. So our header files are always in the double quotes, that random.h, and then we typically use a strategy of having capitalized verbose names. We don't throw away our vowels. We try to make a little bit of sense. So it tends to describe the action that's being taken, that draw a line, get an integer, and so on. So today what I'm going to look at is I'm going to look at one of the 106 libraries here at the beginning, just because it's a nice, easy one to get our head around. I'm going to go and look through the C++ string library. And then I'm going to hopefully get a chance to even start talking a little about the C++ stream library. And along the way, there'll be 2 additional 106 libraries that help out with string and stream that provide a little bit more functionality than what's already there. So randomness. comes up in all kinds of simulations and game playing, right, is that you want the computer to have simulate some random behavior, flipping a coin, rolling a die, or shuffling an array or a deck of cards. Computers actually aren't really capable of true randomness in the sense that you might think in the real world, but they have what's called sort of pseudo-randomness behavior, where it can generate numbers in a sequence that appears effectively random from the outside, even though there actually is some determinism in how it operates. There is a set of library, in our library there are exactly 4 functions that kind of form the cs106 random library that are used for all kinds of random behavior that you want there. I note here that they're free functions, and by free functions I'm meaning that functions that aren't on a particular class, they're actually just globally accessible. You don't call them by sending to a particular object. They actually just exist at the top level namespace, and you can just call them anywhere and anytime. When you're ready to get some random behavior, you make a call to one of these routines. There is an initialization routine for this library, the randomize call. That's called once and exactly once in your program, usually at the very beginning, to kind of set up a new random sequence. So that kind of what's called seeds the generator to get it started in a new place. And then once you've made that call, you can intersperse any number of these calls to simulate certain random events. The standard random number generator that's in C++ kind of provides all of this through just one call. That's just like, well, generate me a random number from 0 to the largest number possible. And then you can decide how to map that to other things. Like if you wanted the ability to flip a coin, you kind of want to say, well, half the numbers are odd and half the numbers are even, or half are heads or tails. You could do something like, well, just generate a number and see if it's odd or even, or see if it's from the bottom half of the range versus the top half. That what these functions do is just kind of provide that functionality kind of packaged up for you neatly. So you can say things like random integer low to high, you say 1 to 5, it'll give you a number from 1 to 5 inclusive. And that is that if you keep calling that, you should see there's a kind of unpredictable sequence of the 1, 2, 3, 4, 5 coming in jumbled and mixing up. No real guarantees about what order you'll see it. That will allow you to kind of simulate random events. The random real, same sort of idea, but in this case using boundaries that are expressed in real numbers and returning a real number. Again, the bounds are inclusive, so it can actually return the number low or high or anything in between. And then the last one is simulating a probability sort of true-false value that given, let's say, the probability of 0.5, half the time it should return true and half the time it should return false. If you give it a probability of 0.25, so 1/4 of the time it'll return true and the other 3/4 of the time it'll return false. So it allows you to kind of simulate coin flips or other kind of random events where you have a probabilistic distribution you're looking at. So the point of a kind of a library, right, is to take some set of facilities that are needed, package it up, kind of have a little bit of a vision for how they work together, a naming convention and a design convention that makes them kind of coherent, that they provide some convenience, right, and that they're complete. They kind of cover all the bases. So these three provide a pretty good range of different kinds of random events. And there's still other things you might need to simulate, but you can typically do it in terms of using one of these. You could also have kind of left one out and have to simulate the others from it. But each of them actually kind of has a client use that's pretty handy, so it actually kind of has all 3 of them for your use. And so that comes out of random.h, right, in the cs106 library.
What is .h?
The what?
What is .h?
It is random.h is the name of the file.
What is .h?
The .h is actually just a convention for the extension for header files, like .txt gets used on text files and .cpp gets used on source files. .h is for header files, which are descriptions of kind of routines, but no real code typically is in the .h file. It's an interface file, they call it. So in Java, right, there isn't that distinction, right? Everything is all in one file. The definition of a class serves as both the description for a client using it as well as the implementer implementing it. In C++, those things are separated. So let me look at C++ string as the next example of something we have to make use of in getting things done. The C++ string type is actually defined in a header file, and it's a library that's added into the language. So unlike int and bool and double that really are kind of part of the language and really can't be separated from it, string is kind of an add-on that's defined through a library. It models a sequence of characters, and characters including everything, letters, numbers, digits, punctuation, All those things are characters. And the string is actually defined as a class. So in the same way that in Java you're used to the idea of the class being the pattern from which you can declare and initialize objects that then you can message and do things with, string in the C++ world is the same sort of deal. You have a string class, you initialize string objects, you send messages to those string objects to ask them to do things for you. Asking a string to give you the character at a particular position, or the number of characters, or to insert some characters or change some characters within the body of the string are all done by messaging the string. A couple simple operations. So I put a little bit of string code just to get started, right? The variable name is actually string itself. There is something a little bit different about string when you declare it and you don't initialize it relative to the things we know about primitives. That when I say string s and I don't say anything else, I have an s equals or any kind of initialization there, you might assume that then, similar to the primitive types, right, that s is just garbage. It has some sequence of characters, 10 characters, 20 characters, 2 characters, with garbage characters in there. In fact, actually, the string has what's called a default constructor, one that's invoked when you don't specify otherwise, such that when you initialize a string with no other explicit information, it will assume you meant to set it up to be the empty string. So making a call string s actually declares and initializes a string with no characters, kind of empty double quotes. So if I were to ask it for its length, which is the way we ask for the number of characters in it, right, that's being used right here, for example, s.length, and then close the open paren there, would return 0 on the empty string. We can use square brackets, like the array notation you're probably familiar with, to access individual characters of the string. So applying the square brackets to s sub I, sometimes I'll call this, right, access the ith character within the string. The characters indexed starting from 0. So if I have a 10-character string, they actually are indexed 0 through 9. And the C++ string, the square brackets allow you to access that character both to read it and to write it, to change it. So a C++ string is mutable. The Java string is immutable, that once you create a string, right, it has a certain sequence of characters, and although you can make a new string and overwrite that one, you can't go in and just manipulate the string in place and kind of change its contents. C++, you can do that. So I initialized string in this case to the string literal or string constant cs106, and then I ran a loop over the index of the proper range of indices for this string, and then I used the toUpper, which is a function from the standard C library that takes a character and returns its uppercase equivalent or unchanged if it's not a letter. And then it assigned s sub I the result of toUpper. So the effect of this was for each lowercase character in the string, we overwrote it with its uppercase equivalent, and any other existing uppercase or punctuation characters just got were left unchanged, right? So actually can make assignment right into that, which is something you cannot do in with the Java string. Question here.
Could you insert like between two characters?
I certainly can. I'm gonna show you that in about 2 slides, but there's a whole set of member functions that then do these things like, so this one allows you to kind of just, given you have this sequence of 5 characters here, go in and mess with them. It's like, well, what if I want to put one in the middle? I'll use something called insert. If I want to take one out in the middle, I use something called replace or erase to pull it out and put something else in. Many of the built-in operators, so things like equals and less than or less than equal to, not equals, have extended meanings that apply to strings when they're used as the operands for those types. So I can assign 2 strings using equals. If I say string s equals t, as I'm doing right here, right, then whatever value t is the 5-character sequence hello, s becomes a copy of that. And now s and t have the same value, but they're not related in any important way going forward, right? We have 2 copies that both happen to have the same 5 characters. So, for example, the first thing I did after this was change the first character of t to be j. So now t is jello, s is still hello. So it was initialized from the same sequence, but they don't retain any kind of aliasing from that point forward. I'm able to compare 2 strings directly to see whether they're lexicographically equal or less than according to ASCII ordering. So I can say if s equals t. In Java, that didn't do what you wanted, right? It did compile, but it didn't test the thing you were hoping for. In C++, it does do what you're expecting, which is to say, take 2 strings and really say, do they have the same sequence of characters? So if I have assigned s to t, if I do s equals t, it's going to say yes, right? They have the same 5 characters in the same order. Once I've changed one of them, right, then they'll come up as not equal. I could do less than and less than or equal to see whether in ASCII ordering which one precedes the other, to do kind of sorting of strings. So just like you think of as kind of like the integer types and in double types, right? Those operators have reasonable meanings applied to strings. The plus and plus equals, right, it's what's called overloaded, so extended beyond its usual meaning for addition to do concatenation of strings. So I can take S and I can add to it a character space at the end. So now instead of being just hello, it's hello space, right? I can also add strings to strings. So I can take T and I can use, let's say, the shorthand plus equals, which takes jello and turns it into jello jello there, attaching another one on the end. The concatenation for the C++ string only operates on strings and characters, though. Whereas in Java, right, there's this kind of automatic mechanism where things like doubles and integers are converted to string and added into the concatenation. That does not happen in C++. So concatenation is just for strings and characters. If you have something that's in numeric form and you want to add it into a string, you'll have to first convert it to a string. I'll show you a routine that does that a little bit later. Over here. Yeah.
Slides available.
Sure. Easy enough to do. I'd be happy to do that. There's most of the things that I'm talking about actually are in the handout 4 as well as repeated in handout 10 and in the readers. So you got like a million places you can look for information on strings, but no harm in having one more. Most of the heavy lifting on the strings is done via these member functions. So these are part of the string class, and so these are operations that apply to string receiver objects. So they're not free functions. You can't call them outside of a usage where you're saying, on some receiver string, apply this function using these arguments. So, for example, the length member function is applied to a string. Just to note here, the word member function is vocabulary-wise the same thing as method, that Java programmers tend to call the functions that are defined as part of a class methods. C++ programmers tend to call them member functions. They really mean the same thing, but I do try to use the word member function because we are a C++ class, and that is kind of the convention. But I'll probably end up using both accidentally without even noticing it, but hopefully it won't cause you too much grief there. So the member function here saying stir.function args is saying apply the function, send the message function to this particular string with these arguments and then get its answer back or have that operation happen. So I can ask a string for its length. Turns an integer, tells you the number of characters. I can ask a string to look for a particular character or a particular string sequence, substring, within the characters that string maintains right now. It will return the index of the first occurrence found, scanning from left to right, or a string : npos. It's a little bit of a funny return value, but it is the return value that says I didn't find it. And so string : npos is kind of an integer value that is distinct from any other valid index within the string itself to tell you it didn't find it. Both of these have a default argument on them. We talked a little bit about that last time. And if I do not specify that second argument when I'm making a find call, then it will assume that you want to start looking from the beginning, position 0. If I do specify it, then it will start from that position and scan from there to the end of the string. So it's a way of targeting the place you're looking for it a little more precisely than just starting from the beginning and going to the end. C++ does allow what's called overloading. In this case, the function find that finds a char and the function find that finds a string both have the same name. And so that name can be used for multiple purposes as long as there's a sequence of arguments that distinguishes them so that when I make a call to find, it knows whether I meant the first version or the second version by virtue of whether the first argument is a character or the first argument is a string. And that can be extended to other types. This is typically used when you have an operation that really has the same behavior, but just some slightly different sequence of arguments is required to invoke it. It is not something you'd want to use a lot to make a bunch of similarly named functions that don't have similar operations. So it just allows for a convenience when there's 2 or 3 variations of the same theme. They might all come under the same name by virtue of overloading. And then these are ones that, well, maybe I'll do substring first and then I'll mention these are all kind of together. Substr is something that, given a receiver string and a position and a length, will extract a new substring out of the middle of the string that was received. So if I say to the hello string, starting from position 0, take 2 characters, I get the string he. It copies them. It's distinct from the original. And so all it did was kind of get its initial sequence by copying characters from there. But if I go on to change the hello string into jello, right, that he string stays he. So they're not attached in any long-term way. Then insert, replace, and erase are all of the family of something what I call modifiers or mutators that change the receiver string. You can send these messages to a string to cause new text to get added into the string, text to be removed, or text to be kind of deleted and replaced with something else. So inserting, so someone asks, well, how can I put new characters in the middle? Well, I put the position where I'd like them to go. If I say position 0 and I say put the string I in there, then it would bump everything down and put I in the front and replace it. So if it was hello, it would be I said hello. Let's say I inserted the string I said. The replace, right, at a position removes length character starting at that position and then replaces it with that character. So a way to kind of take a chunk out and put something else in its stead. And then erase, which just does a straight remove. Add a position and a particular len, take this number of characters and throw them away, deleting them from the string, making it shorter. So all of these change the receiver string. When you say stir.insert, stir.replace, stir.erase, that after that call, stir now actually has new contents based on what you've asked it to do about changing and mutating its context. So here's something I should tell you a little bit about C++ string relative to the Java string, is that C++ being kind of an industrial strength language that's targeted at professional programmers does not make any guarantees to you about what happens if you misuse these calls. So if you give it a position that isn't valid for the string, or a length that isn't valid for the string, that there is no contract in the C++ libraries that said, well, this is what will definitely happen. It doesn't say, oh, it's definitely going to throw an exception or throw some sort of error. It doesn't say, well, it's just going to truncate at the end. It says that the library is free to do whatever is convenient for it, up to and including just crashing. So it does mean that as the programmer, right, kind of using these calls, it is a little bit more on you to be careful that you're using them correctly, that you're making the numbers are in bounds for the string and things like that in ways that will produce correct results. That it might be that it will produce a nice error message, but no guarantees, and so you wouldn't want to come to depend on that. We want to just be careful about knowing what the right numbers are. So unlike Java, right, which is very attentive to those sort of things and kind of on your case when you're a little bit out of bounds. In the name of efficiency, it tends to just breeze through that stuff. All right. I'm going to show you, let me just go in and we'll do a little bit of coding in this together, just for fun. Just because I like to sit and show you some things. Just a little practice with some code. So if I were to do something like, let's say, want to count the occurrences of a particular character within a string, right? I could write a loop that looked like this. I could say int, count equals 0 for, and this is a kind of very ubiquitous loop, right, for operating over a collection, in this case the collection being the characters in there, right, from 0 to this length. And if s sub I equals the character I'm looking for, right, we would increment the count and then return it. And so I could put this down here in my code and do a little testing of looking for the character, let's say C in Chihuahuas, I can't spell, Chihuahua cheese crackers. You guys probably don't read Skippy John Jones, but I do in my house every night. So I know about these things. So let's take a look at that and see if we actually managed to count the number of C's in my list there. So there's 4 apparently. Let's go check and see if that kind of comes out. Chihuahuas, cheese, crackers. Oh, looks good. Okay, so we did a little bit of counting and we're feeling okay about that part. And then let me do something where, for example, I want to remove all the occurrences from that. And I'm gonna write this 2 different ways just to highlight a little bit about how things work. So I'm gonna design a remove occurrences that, given a character in a string, will return to you a new string where all the occurrences of ch have been removed. Seems easy enough, right? So it's not going to modify the original string, it's going to actually return a new one. So here's my strategy, and this is often the way to build these things up, is I could go through the kind of manipulations of kind of, try to take the characters out in place and figuring out where I'm at, but often the easier way to do this is just to build up the result, right? Decide when to append or concatenate a character from the original string and when to ignore it and go past it. So I can do something like this, where it's like, well, if the character I've just seen is not the one that I'm trying to avoid, then I can just add it into the result. And then when I'm done, I have the result. So if I do this and I change this call down to remove occurrences. And so I'm counting on, for example, the fact that result is initialized to the empty string. So you notice I didn't actually say anything there. I could, for example, do this, and that doesn't change anything about it, and you might feel a little better about seeing that explicit initialization, but C++ programmers are very used to seeing uninitialized strings, knowing that that means that they got the default initialization to the empty string. And there, when I didn't find the character I was looking for, right, I append it to the result. I'm going to switch this up just a little bit, and I'm going to change remove occurrences to, instead of making a new string, to actually modify the string that I have. So I'm going to change my code down here to match what's going to happen. I'm going to set it to be this. And then I'm going to call remove occurrences, C of S, and then I'm going to print out S afterwards. So this, in this case, I don't expect there to be a second string created. I expect us to go in and modify that string in place, kind of truncating some of those characters, taking them out to make this work. Okay. So I could kind of do this thing where I'm kind of walking down the string character by character and then deciding whether to collapse over it. I'm actually going to just change my strategy entirely just so I have a little practice using some of the other routines. And I'm going to end up using the string find. So we'll start with this. I can actually do this. S.find of ch, and if I don't give that second argument, it's going to start from the very beginning and look all the way through and see if it finds it. I'm going to put hold that result in a variable, and I'm going to say while found equals the result of calling find, and then I'm going to stick it in. This is a very kind of C++ way of coding, right? Is kind of tightly combining this up, but in this case I have an assignment, right, and a comparison all in the test of the while loop. So I'm making the call to ask the string to find a particular character, storing that result in an integer here so I can use it, and then comparing that result to string npos. So the string npos is a little bit of a funny C++ syntax there, but it is the way to read that is within the string class. So string : says within the string class, kind of scoped within string, there's a particular constant called npos, which is used as the return value in cases like find when it's looking for something. And that npos being part of the class is sort of a way of avoiding it conflicting and interfering with any other usages where you might have variables named npos or similar functionality. It's kind of tied to the string class through this scoping mechanism. So I check and see if it's not string npos, and then if it's not, then I go into the loop here and I can do an erase of one character at position. So erase takes the position in the count, and it just removes the number of characters I specified from that position, and then it'll come back around. I have passed string by reference coming into here, and that's a very important part of what's happening here because these calls to erase that are modifying string, if I have not passed string by reference, right, they'd be operating on my copy, and I'd go through all the trouble of erasing all the C's in my copy, but when I got back out to the main call, none of those effects would have been permanent. So passing by reference really means that what remove occurrences got was access to the original S, and maybe I should even make these names. I'll call this my string out here so that we don't get any confusion about the two names here. The my string variable in main is really being accessed by remove occurrences without a copy. It's reaching back out into main, and it's really making changes to the my string itself, taking its C and deleting it down. And so let's finish the fix to that. What does it not like about that? Oh, pause. Yeah. What did I call it? I called it found. Yeah, well. Okay. So Wawa's he's and wreckers, right? Still looking good, right? So I achieved the same thing, but to a different effect. And that's one of the things about the string library, right? Is it's so big and it has so many different ways of doing things that often, right? 2 people, or 10 people running the same task won't even come up with the same solutions. I could have used a replace, right, where I replaced found the one character it found with the empty string, right? I can build it up through concatenation. I can take it down with erase and replace, or I can insert the other way around. Bunch of things I can do that in the end will achieve the same effect, but just show that there's a lot of different ways to accomplish the same things because the library is pretty rich and has a wide variety of tools in it. I'm going to make one change to this just to show you how I can make it just slightly more efficient. Now this is kind of silly because strings are typically very short, so it doesn't really matter. But I'm going to do this, and I'm going to use found as my index on subsequent calls. So I can say starting found from 0, do my search from 0, and then found, and then any subsequent calls will pick up where I left off. So the next time around through the loop, right, found is at the place where I found a previous occurrence of that character, and it says, okay, starting from that position now, look forward and see if you see any more from here to the end. And so for a very long string, right, this ends up actually doing a lot less work, where it doesn't start all the way back at the beginning each time. It just picks up where the previous occurrence was found and goes from there to the end. So small change, but no big deal. Hey.
Could you explain again the string colon and pause?
Yeah, so string colon is just, basically what you're saying is find needs to return something to you that says I didn't find it, right? It could return to you 0, 1, 2, 3, all these indices. It actually needs to return to you in this, it uses a special sentinel value that says I didn't find it, and you might think that might be -1 or some other thing, right? A good programming form though would be to have a constant for it, right? So that you don't have any magic numbers embedded in your code, and that constant is defined as part of the string class. And so that just the syntax for accessing that constant out of the string class is using the string class name : npos. So it's basically the syntax for I have a constant that was defined within a class. How do I get to it? I use its class name, 2 colons, and then the name of the constant. And it's just C++ for something that in Java looks a little bit more like class name dot. Question?
Sometimes I see a function declaration before main and then the definition afterwards. Is that just a matter of preference?
It totally is, right? So partly I'm being a little bit lazy in class, right? Which is if I put the function definition up here, then I can call it down here because it's already been seen. If I put it down here, then I need a prototype up there. And then the prototype means I have to be a little bit more careful. When I change the name, I got to change it in both places. If I change the arguments, got to change it in both places. But the problem, of course, is that when you read the code, it probably reads a little better to say, here's the main, which makes calls to A, B, and C, and have A, B, and C down here. And so some of it has to do with, well, it's a little bit harder to maintain in that form, but I think it's easier when you're done to read it. And so you're totally free to do it either way. You probably just ought to pick a strategy and go with it. That the maintain the prototypes is not really that much work once you get used to it. And I think in the end, it probably is a little bit cleaner. But when I'm being lazy in class, I'm much more likely to just throw them up there to save myself some time. That's a very good question, though, because it's good to note. There's a lot of things that probably will slip by me if I'm not being careful, and you want to be sure to call me on it if I'm not giving you the right information. So let me go back and pick up. There's a few last little details about string that I don't want to overlook before I move away from this. So that there are this library of functions, and I say need to know, right? I have them kind of sketched out in a couple places, and that you can kind of look at them and see what they do. Kind of knowing they're there, and then learning about them as you encounter them is a fine strategy. There are a couple additions in our stir utils, which is a 106 specific header file, which are just some things that, for one reason or another, are a little bit harder or more annoying to do using the standard tools than we think is worth putting on your plate for now. And so we have two convert to upper and lower case that, given a string, just convert it to its upper and lower case equivalent. And some things that do conversions between string and integer and real, and between string and integer and string and real when you have it in one form and you need it in the other. Here's something that just does that for you as part of the string library. So just some simple things that you might find yourself needing, and you just want to know they're there. So here's something that actually is a little bit of a bummer. Part of the legacy, right, of C++ being built on C means that every now and then there's a little bit of the history, kind of in our deep, dark past, that pops its head up in ways that are a little bit surprising. And for string, it turns out there is a little bit of a weirdness here that I want to point out before you run into it the hard way. That there is a notion of the old style C string. So the original C language didn't have a string class. It actually doesn't have any object-oriented features at all. And it did have, though, some other more primitive handling of sequences of characters, because this is a very common need, right, is to have something. Now, I put in parentheses what it actually is. It's a pointer to a character array that's null terminated. Don't worry about what that phrase means if it doesn't mean anything to you, but that's just for those of you who've seen it a little bit before, I'm just reinforcing that, yeah, we're talking about the same thing. That would be fine. We have this better string object that has all these fancy features, so you'd think we could just use that and ignore the fact that the other one is there. It almost, 99% of the time, that's exactly how it's going to work. But it does turn out that there are a few situations where this old style string kind of pops its head up and gets a little bit in our way. One way that may be a little bit of a surprise is that the string literals are actually C strings. That when you see an open quote, some characters, and then a close quote, that the compiler interprets that as a C-style string. Okay. It also, though, has a mechanism by which if you tried to use it in a context where you needed a C++ string, it will just automatically convert it for you. So it'll take the old style string and make a C++ string out of it. So okay, so that means that basically I can just use them wherever I wanted, and it seems like it'll mostly work out. There is a way you can deliberately force it. If you use what looks like the typecast here, this is actually calling the string constructor, and you pass a string literal or string constant. It'll turn it into a C++ string manually there. Okay, and then like, well, it's going to turn out that you might need to know this, right? And then there's also the other problem of, well, what if I have it in one form, I want it in the old form? So this is, I have the old form, I want a new form. I have the new form, I want an old form. There is a member function on the string class that will return to you an old style string from a new style C++ string, and it's called the C_stir routine. Okay, so they let you convert. Why do you care? Well, it turns out there's one thing you'll definitely run into, which is when you're opening a file, this will come up probably not today, but certainly on Wednesday. You're opening up a file stream and you want to say, this is the file on disk that you want to identify. It turns out that that library requires the use of a C string as the name. It's just kind of a part, there was a little bit of an issue trying to get all the libraries to come together at the right time. And it turns out the stream library got finalized before the string library was done. And so it depended on what was available at the time, which was the old style string. And so even years later, when they're both happily, debugged and working and everything, it is still the case that when you use the stream library, you're trying to open a file, you have to describe the file you want by using the old style string. So if you had a C++ string variable that held the name you wanted, you'll actually have to convert it. Converting in the other direction comes up pretty much in one case, and I'm going to show you this one. It has to do with concatenation, that the plus operator that does concatenation really wants to work on C++ style strings. So if one of your operands is a C++ string, it's all fine. As long as the left or the right side is a C++ string, it's good. Then the other side can be a string literal, a constant, another string, a character variable. All those things work fine. So as long as at least one of the operands really is a true C++ string already, you're good. That's almost always the case. But in the case where you somehow have two things on either side of the plus, neither of which is already a C++ string. So typically that means you have a C string on one or both sides, a character on one or both sides. You are not going to get concatenation. If you try to add two C-style strings, right, it actually won't compile. Thank goodness, because that'll help alert you to the problem. The sad thing about these two things, about taking a string literal and adding either a character constant or a character variable, is that it does compile and it just does not do what you want at all. And it does so in kind of a silent but deadly sort of way. I'm not going to tell you really what it does, but if you are curious, you can come and talk to me and I'll lay it out for you. But what I want you to come away with, right, is just this memory that when I'm using concatenation, that to be sure that one of the two operands is a string, a C++ string, if you have to, force one, right? If you have a string literal and you want it to be a C++ string, then make it one to avoid running into this. Because the mistake that you get from this is actually quite mystical and very confusing. I'd like to say, really, probably 95% of you would never run into this, and so mostly I've just confused you for reasons that seem kind of unclear. But for the 5% that we're going to run into this and then not have any idea where it came from, I'm really trying to do you a favor by giving you a heads up before it causes you a lot of grief later. So just kind of a little bit of a legacy, right? C and C++, right, kind of go back a long way, and as a result, sometimes we have these little quirks we have to deal with even in the modern world.
Is that the only way you can convert a C string into a C++ string?
Not exactly. I mean, a lot of times it just happens automatically is the truth. In almost all situations, like if you had a routine that expected a string argument and you passed it a string literal, it'll automatically convert. So mostly you won't need to do this is the truth, right? So it happens all the time behind the scenes without any effort on your part. But this is the official way to say, I've got a string right now and I really want to force it and I'm not waiting for the compiler to do it on my behalf. I need to, in particular, for example, in a situation like this, it doesn't realize what you really wanted to do was convert this and do concatenation. It does something kind of goofy based on what the old meaning of taking a C string and adding a character to it was, which was not concatenation. Okay. So that's just a little moment of silence for sort of an old language C that comes back to haunt us a little bit like a ghost in the attic. All right, so let me tell you, way in the back.
What exactly do you mean by a string literal?
So a string literal just means a string constant. It just means something in quotes.
Okay,
so
without explicitly declaring it to be a string.
Yeah, so string literal is just like when you see open double quote, some characters, open, close quote, that's a string constant or a string literal. So in any situation where you see exactly that, not a string variable, is basically what I'm saying there. Anybody else before I give you a little taste of I/O, which we will get started on today, but we'll have to finish on Wednesday, is, well, how do we do I/O? How do we do input-output in C++? So let me first off say that input-output is probably one of the more distinctive features of any language. C's I/O, for example, looks very different than C++'s I/O, which looks actually kind of different from Java's I/O, which looks different from Lisp's I/O or Python's I/O. That these are one areas where, for some reason, even though they all do the same things underneath it all, right? They let you print stuff, they let you read stuff, right? They have some formatting features. For one reason or another, these are the areas where they're just widely divergent in their syntax and the way you express what you want to do. That makes them particularly annoying to learn, is the truth. Like, I know a lot of I/O systems, and they're all very jumbled up in my head. At any given moment, if you ask me, how can I print a decimal number with 3 digits of precision in this language, right? I'm going to have to go look it up. And so that's, as my model is, yeah, look it up. Don't worry about memorizing these details, because they are very, tied to any particular language in its formatting system, and on an as-needed basis, right, kind of flesh out the details that you need to figure out how to solve your problem. So for that said, we're going to use a little bit of I/O. We'll need to be able to read and write things to the console to interact with the user. We're going to do a little bit of file reading, reading numbers and strings from files, maybe even producing some files. We're going to use some very simple set of features, not going to go too deep, and certainly when you need to know more, there are great resources to go check into for that, but I wouldn't in advance go make yourself an expert on any form of I/O. Let it figure it out when you need to. So the I/Os are actually handled in C++ using stream objects. There are stream classes. The O stream is the output stream that's used for writing. The I stream are the classes used for reading. There are variants, for example, the IF stream and the OF stream that are the file equivalents of the input-output streams. Cout and cin are these two basically global variables, effectively, right, that give you access to the console output stream, and cin for the console input stream. And that means the little text window that pops up that you get to type and print things for the user to see and interact with. And then the standard operators for kind of reading and writing to the stream in the default sense are the less than, which is stream insertion, and greater than, which is stream extraction, which allows you to stick things onto a stream and then retrieve things back from a stream that you're reading from. So a very, very simple example of this would be like, I have the variables x and y declared here. I ask the user to enter 2 numbers, and then I use extraction that says from the console input stream to pull an integer out followed by another integer, and then I repeat back what they said. And so in its simplest form, right, the kind of things you can print out are very related to things you can read in. When I ask cin to read an integer here, it looks for a sequence of digits upcoming in the stream that form a valid integer, which it assembles and puts into the value x, and then it looks for another one. It typically uses white space as the delimiter, so any returns, tabs, spaces, right, will be kind of skipped over in between. So anything that led up to x, it'll skip over all the white space, look for some digits, right, and then skip over any intervening white space, look for some more digits to pull y. Of course, what's likely to happen here is users are bad typists. They make mistakes that when I go to read this, what happens if they've typed the letter A here, or 72A45, something where there's a letter in the middle. This causes a little bit of havoc, because when it goes to extract that, it looks for some digits and it finds this thing and it doesn't match its expectation, and that kind of puts the stream in what's called an error or a fail state, which then requires you kind of digging around, realizing it went into a fail state, cleaning it up, and kind of resetting and starting over. It's not that it can't be done, but it's just a little bit annoying. So we just made this task a little bit less onerous by providing in the SimpIO library, which is our cs106 simple IO. It has get integer, get real, and get line. And they all read from the console, so reading from cin, and they deal with all that error handling. They make sure that what the input that was given was well formed. If it's not, it reprompts and has them try again. It does that until they get an integer. So when you call get integer, you know that eventually the user will have typed in a well-formed integer, and you will get that value back when you make that call, and you don't have to be worried about all the machinations to check for errors and retry. Is actually bundled up behind that routine for you. So most of our console input, right, will end up using these functions just for convenience, right? They save us a certain amount of hassle. Question?
But in the get integer case, you would have to split it up into 2 numbers.
Yeah, so I would have to, if I wanted x and y, I'd have to say get integer 1, get integer, I have to call it twice, right, to get those 2 calls. So there's not a, kind of combined form of it, but But it saves us a lot of trouble, it turns out, other than, because really I can't do it this way. I have to stop after one anyway, check to see if it failed. If not, go back in and stuff. So in fact, it's kind of misleading to even show this form, because that form assumes that the user is a perfect typist and never makes a mistake, which is, in this day and age, not too likely. So. Okay, I have more things I'm talking about file streams on Wednesday, but no reason to kind of stuff it in the last minute and a half here. So on your way out, look for handout 5 and 7 for Mac or PC, depending on what you're using, and good luck getting your compiler set up. I'll see you on Wednesday.